We're now going to turn our attention from chemical kinetics to a closely related topic, which is chemical equilibrium. Notice that chemical equilibrium applies to a new concept that we have not talked about prior to this point. It applies to something known as reversible reactions. This information in Chem 2A is found in Chapter 10, Section 10.2. So what is a reversible reaction? Well, as the name implies, a reversible reaction would be a reaction that proceeds in both directions, meaning that the reactants can undergo a chemical change to form products, which we have been talking about up to this point, but the products can also undergo a chemical change to reform the starting reactants. So we can represent that here with this notation where R stands for reactants and P stands for products. And up to this point, we've only been considering a situation where reactants undergo a change and form products. But some reactions, especially biochemical reactions, are reversible reactions. And once you form the product can undergo chemical rearrangement and reform the starting reactants. And of course, whenever you have a reaction, you have a reaction rate, what we looked at with kinetics, applying to it. So we can now discuss two different rates of reaction. The rate of the forward reaction, where reactants form products, and the rate of the reverse reaction, where products reform the reactants. Usually when we look at chemical systems, we imagine a situation like I have graphed here, with concentration on the y-axis and time on the x-axis. And usually we imagine a situation where we're starting with only reactants, so a significant amount of reactant, and the brackets refer to concentration. So when you see the R with the bracket, we're talking about concentration of reactants. And the products, bracketed, concentration of products. So this graph is showing a situation where we're starting with a significant amount of reactant and no product present, which is what we usually imagine or think about when we approach a chemical change. Well, what happens over time? Since you only have reactant present, the only thing that you can do is the forward reaction. You can't have any reverse reaction happening because you don't have any product present. So the rate of the forward reaction is going very fast initially, and there's no reverse rate happening at all because you don't have any product present. But what happens over time, as we can see from the graph, as reactants change into product, their concentration drops, and as you start making product as a result of the reaction going in the forward direction, the concentration of product increases. Well, we know that reaction rates depend on concentration. So as we use up reactants, what happens to the rate of the forward reaction as the amount of reactant decreases? It goes slower and slower and slower. And what happens to the rate of the reverse reaction as you start making more and more product? Well, it goes faster and faster and faster. So we see this change in concentration happening over time. What happens when you reach the point where the rate of the forward reaction is going just as fast as the rate of the reverse reaction? Well, if that point is reached, you're taking reactant and forming product as rapidly as product is reforming reactant. Once you reach that point where the rate of the forward and the reverse reactions are equal, then you can't be observing any net change in the amount of reactant and product. As fast as reactant is changing to make product, product is reforming the reactant in that same rate. So you see no net change in the concentration of reactant and products. And that's why these curves, instead of continuing to change, flatline and reach what we call a steady state, where the concentration of reactant that decreased initially over time reaches a value where it holds constant. The concentration of product that increased over time initially reaches a point where it flatlines, holds steady and constant. At this particular point, where the concentration of reactant and product are staying the same and not changing, at that point in time, you have achieved equilibrium. So from this point onward, if you just allowed the chart, the time graph, to go on and on, you would see no further change in the concentration of reactants and products. You are at equilibrium. So let's give that definition of chemical equilibrium. It is that point in a reversible reaction where the concentrations of reactants and products, again, these bracketed letters here refer to the concentration of reactant and product, where those concentrations remain constant. They no longer change as a function of time, as we're observing here on the graph. When is chemical equilibrium reached? Chemical equilibrium is reached, or it occurs, when the rate of the forward reaction is equal to the rate of the reverse reaction. Once you're at this point, equilibrium is reached and there's no further net change in the concentration of reactants and products. Some notes about chemical equilibrium. It's achieved over time, as our graph is showing. We're not initially at equilibrium, we achieve it. So rarely are the starting concentrations of reactants and products also the equilibrium concentrations. So rates of forward and reverse reactions will not be the same initially, but as the concentration of reactants and products change over time, their reaction rates change for the forward and reverse reactions. And once we reach the point where the rate of the forward reaction equals the rate of the reverse reaction, equilibrium is reached or achieved. And we have this term called dynamic equilibrium. And it's called a dynamic equilibrium because things are still happening. Chemical changes are still occurring. But because these changes are occurring in equal and opposite directions, there's no net change in the concentration of reactants and products. Note that reaction rates are what is equal. So the equal part of equilibrium, or the equa part, refers to reaction rates, not the concentration of reactants and products. Rarely will the concentration of reactants and products be equal at equilibrium. And this graph is illustrating that point as well. Once equilibrium is achieved, we see that the concentration of product is greater than the concentration of reactant in this particular example. But the reverse could be true as well for some reactions. Some reactions, when they reach equilibrium, you have more reactant present than product. So it just depends on the reaction that you are looking at, whether when you achieve equilibrium, do you have more product present? As we're showing in this graph, the amount of product higher than the amount of reactant, or concentration of reactant at equilibrium, or is it the reverse situation? It varies from reaction to reaction. In order to get a better idea of that, I should mention here in this introduction to equilibrium that because the concentration of reactant and product remain the same at equilibrium, you can calculate what is known as an equilibrium constant, symbolized with a capital K, referring to constant, so not changing in value. And the equilibrium constant is calculated by taking the concentration of products and dividing them by the concentration of reactants. It's a little more complex than that, but that's beyond the scope of this particular lecture. But in general, if you take a look at equilibrium concentrations, where this refers to at equilibrium, not initial, but at equilibrium. If you divide the concentration of reactants, which are staying the same, by the concentration of products at equilibrium, which are staying the same, by the concentration of reactants at equilibrium, which are staying the same, if these values are the same, then you must be calculating a number that is also staying the same and not changing. So K, capital K, refers to the equilibrium constant. And note, if K is a large number, well, the only way that you can get a large number from this calculation is to have the concentration of products greater than the concentration of reactants at equilibrium. Numerator greater than the denominator gives you a number definitely bigger than 1, and the larger the value is, the more we understand that the equilibrium lies to the right. And what does that mean? At equilibrium, right referring to the product side, the right-hand side of this equation, left referring to the reactant side, the left-hand side of this equation. If K is a large number, then the equilibrium lies to the right, and you will have more product than reactant at equilibrium. In the same vein of reasoning, if the equilibrium constant is a small number, the only way to get a small number for K is to have the denominator bigger than the numerator, dividing a small number by a larger number. So the concentration of reactants is greater than the concentration of products at equilibrium. If K is a small number, the equilibrium lies to the left, and you have mostly reactant present at equilibrium, written to the left side of the chemical equation.